All right, thanks for the introduction. Yeah, as said, I'm going to talk a little bit about work graphs, how you can use it. So first part, and in the second part, we're actually going to take a look, a sneak peek sort of under the hood and see how work graphs actually works on our AMD GPUs. But first, let's start with a little bit of context. There has been some general buzz around work graphs ever since the initial preview phase a bit more than a year ago, and early this year, on March 11th, the first 1.0 release came to the DirectX 12 specification. At GDC itself, we showed a small extension to work graphs, which brings the sort of long-lived dream of many graphics programmers that they can now issue draw calls directly from the GPU to reality. And earlier this month, we sort of brought this dream to everyone with the Mesh Nodes preview, which you can try right now. And AMD has been supporting all of these releases with a driver right from the get-go. And today, we've just seen a first talk on content you can do with work graphs. There's a poster back there with work graphs, and you've seen it come up in multiple talks already. So what is all this buzz about? Well, today, if you want to program on the GPU, you're probably going to use one of these graphics APIs or something very similar. And these APIs are very nice. They give us access to quite a lot of features that just show how powerful GPUs have gotten in recent years. So we have, for example, different ways of rasterizing a scene, all the way to hardware-accelerated machine learning. But all of these graphics APIs have sort of one limiting factor in common, is that whenever we want to do something from the GPU, on the GPU, we have to explicitly tell it from the CPU to do something. So while the GPU itself have become quite powerful, they can't really decide themselves on what they want to do, at least not yet. You might say there is execute indirect, and you could create new work with that for the GPU. And yes, that's at least partially right. You can create work with execute indirect on a GPU and then execute it on a GPU, but you still need to explicitly tell the GPU to do so from the CPU. For example, you have to set your pipeline state, and then you have to tell the GPU, hey, this is where you just created some work, go execute that one. And if you try to do anything complex with it, you'll also have to deal with like a forest of barriers. And even more additionally, if you want to sort of have some data to go along with the work you've created, you also have to write a memory manage of some sort for that. So what are work graphs and how can they help us solve this problem? Well, work graphs are producer-consumer networks of work items flowing through a graph of nodes, all happening entirely on the GPU without any sort of intervention from the CPU. There is a lot of information in that one sentence, so let's try to sort of unroll it piece by piece and maybe start with the last part, the nodes. Because typically when we programmed the GPU, we were using shaders. So what are these nodes now? And to sort of get to the bottom of that, we're going to take a look at one example shader. In this case, we sort of have some material shading. So we have a simple compute shader with 8 by 8 threads. And we can dispatch multiple of these thread groups to process an entire full screen texture. And as we're doing material shading, we can load some sort of material ID from another texture that has been outputted before by, for example, a rasterizer, compute rasterizer. And then we can use this material ID to decide on how we want to shade that particular pixel. Now, this approach is often referred to as an Uber shader and has quite a lot of downsides. For one, this shade material shader kernel has the worst case resource allocations of any of the material shaders, the worst case registers, and for example, if you're using shared memory or something. In addition, the switch case statement, GPUs don't really like that. There are a lot of divergent code flows in that. So we're looking for something better. And over the course of this talk, we're going to see how workers can actually help us to transform sort of this material shading example into a GPU-driven material shading that's quite friendly to the GPU. So first step is we create a node, and that's very easy. You just write my shader is now a node. And then the next thing you have to figure out is, okay, how do I want to launch this node? And this is the first sort of major differentiator with work graphs from sort of regular compute shaders, execute indirect, or other sort of GPU graph-based implementations, that work graphs does not think in sort of dispatches or launches. Work graphs thinks in work items that are sort of processed by a shader kernel, or a node in this case. And there are different ways of how we can launch a node for a particular work item. The first and foremost is the broadcasting launch. This is quite similar to just dispatching a compute shader, and something you're probably quite familiar with already. And here we just say, okay, each work item gets a dispatch grid of thread groups. The second node launch is the thread launch. The closest resemblance to this would probably be dispatch rays in the DXR ray tracing specification, as this also allows us to have like thread granularity when launching work. And thread launches are also very similar to that one, because each thread in this thread launch node cannot see all the other threads. And sort of one advantage if we're using work graphs is work graphs isn't just going to launch one wave with just one thread working, but the scheduler can combine multiples of these work items and try to fill the entire GPU. And the last node launch, which you heard something before already, is the coalescing node launch. Now, at the surface, this might seem quite similar to the thread node launch in that we have multiple work items going to a single thread group. But in this case, we can actually set how many work items we want to receive and how large this thread group is going to be. And in this case, all the threads can also work together on processing these items. And you've just seen how you can, for example, use it to turn a soup of draw calls into instance draw calls. So back to our material shading shader. In this case, we're sort of porting over a compute dispatch, so we're using a broadcasting launch. And the next thing is we're going to need to figure out how many thread groups we actually need to launch. And there are two ways to do that. The first one is we just write a static dispatch grid to each node. So every time you invoke this node, this many thread groups will be launched. Or the second way is you just write a maximum limit for that, and then have the actual number of thread groups set dynamically by a record. Now, what is a record? Well, a record is just a struct holding data, and a record is, well, the actual work item that's flowing through the graph. The term record and work item are sort of interchangeably used throughout work graphs. So in this case, we just have our three-dimensional dispatch grid telling us how many thread groups we want to launch. It's annotated by a special semantic. And if we want to use this with our node, we can just write it as an input to our function signature. And with this, we successfully created our first work graph node. The problem is we just have one node now. It's not really a graph. And we haven't solved any of the problems with a material shader. So we can sort of rinse and repeat and create a second node. In this case, we just call it shade pixel. And this one will just shade a single pixel. And as it's shading a single pixel, we can use the new thread launch mode, create a record for it, in where we define, okay, which pixel do we want this particular thread to shade. We can sort of then load this pixel information in our node. And for now, let's just copy over the material shading we had before. We'll get to how we can optimize that. If we then want to launch this second node, we can't just call this function. We have to declare it as sort of an output of our first node that we created. And this has sort of some special syntax attached to it. And you can see that if to connect the two nodes, we just use the same name as we used to declare the function name for the second node. And we also need to declare how many records we intend to output from our node. In this case, we have 8 by 8 threads. And each thread wants to write one of those records, so we have 8 by 8 threads at most. To then write some of these threads, there are some new intrinsics functions where you can sort of request output memory for one record from the system. You can then sort of write your data to it. In this case, it's the pixel coordinates, and then you send it off. And this is sort of very similar of some message passing APIs in that you're never going to see anything from that record again. It's just gone. It's going to the system. At some point, the scheduler will launch that node, but you'll never get any feedback from it. So the work graph only moves forwards, and there is no sort of feedback going backwards. And with this, we created a work graph. We now have 2 nodes in our graph. One is the producer, one is the consumer node. And of course, work graphs isn't just limited to 2 nodes. As you see in Bastian's talk, we can have many of them. But there are some limitations. For example, one of them is that we cannot have at most a graph depth of 32 nodes. And there are also some limits to the outputs. You've just seen sort of the output declaration we had. At most, each node can output 256 different records. which means we can in theory also output to 256 different nodes. And total across all of these outputs, we can at most sort of write 32 kilobytes of node or record memory. And of course, this just doesn't have to be sort of a tree-like structure. There can also be multiple nodes targeting the same node. As you've seen in Bastian's talk, recursion is also allowed, but only self-recursion. So you can't recurse between two nodes, and each of those recursion steps will count towards the 32-node graph depth limit. So with these limits sort of out of the way, let's get back to our material shading example and see how we can sort of optimize any of the problems. Because before we just copied over all this bad switch case, worst case resources code to the second node, and we now want to have an optimized implementation. To optimize this, what we really would want to do is we just have one of those thread launch kernels for each of the different materials. Then we can just write the specific code we want to run for each material in there, and have like a bunch of different nodes. And the problem is, okay, does this now win in our producer? We have like a stack of different outputs and run into this 256 output limit very quickly. The answer to that question is no. Workgraphs actually specifically accounts for this use case with a special feature called node arrays. Node arrays allows you to bundle multiple nodes of the same launch type and the same sort of record together. So now we can address them sort of like a single node, but we can still decide which of the which sort of node in this node array to launch. And we'll see that when we look at our producer node. There are some small syntax changes. We have to say that we're now outputting to a node array. For some sort of allocation reason, we also have to say specify the size. But for example, unbounded sizes or sparse node arrays are also supported. And the second small change is when we sort of requested one of these records to write to, we now have to specify the material ID or the index into this node array that we want to write to. In this case, it's our material ID. And you can see that each thread can potentially write to a different node in the array. So essentially what we've done here is we've taken sort of this very bad, very unoptimized code for shading materials and turned it into a nicely GPU-driven material shading with the help of work graphs. And you can see some sort of example how our input to this might look like. Each different color represents a different material ID, and that will sort of get classified into different into the different nodes in our node array. And if you want to learn more about this, you can actually find the sample over on gpopen.com. So with this sort of small introduction on what work graphs are out of the way, you might ask yourself, okay, how does this actually work? So what has changed in GPUs that they now suddenly can start to decide what they want to launch, when they want to launch, and how they want to launch it? And to understand this, we're going to take a look at how work graphs work on the RDNA3 architecture. And first of all, we have to understand how we can launch any work on a GPU. So we're going to take a look at how a compute shader dispatch actually works in hardware. So when we want to launch a compute shader, we sort of write a dispatch command to a command list or record it to a command list. This is very similar for DirectX 12 and Vulkan. And if you're using, for example, OpenGL, that's all hidden by the driver. Once we finished writing all the commands to the command list, we can then submit this command list to one command queue. And this sort of sends it off to the driver and says, okay, please execute this work for me. And we're going to see what happens next. Next, the GPU driver sort of takes this command list that we've given it and copies it over to GPU memory. Obviously, it sort of changes the encoding such that the GPU can actually read it. And then we also need to send the GPU some sort of command of, hey, I've put this command list here in memory, go execute it. And the GPU driver sends this to the GPU through a ring buffer. And if you sort of take a look at what's happening then on the GPU, this ring buffer is connected to a so-called command processor, or more specifically the microengine scheduler, which is part of the command processor. And as you can sort of guess by the name, the microengine scheduler is responsible for scheduling these incoming commands from the CPU and sort of distributing them or executing them on the GPU. And to sort of actually execute some work, the microengine scheduler has access to a lot of different pipes or queues, however you might want to call them. which can then actually execute the work. And those are sort of sorted into graphics queues, which can then, so for example, draw stuff, and compute queues, which only can compute things. And you might actually recognize this sort of split between graphics and compute, as this is sort of also exposed in DirectX 12 and Vulkan. Now, in our example, let's say we just have submitted our command list to a compute queue. So the microengine scheduler grabs a sort of compute queue that doesn't have any work currently to do, and forwards it this command to execute this command list through another ring buffer. Now this compute queue here is sort of a small processor on the GPU that can be programmed by firmware. And in this case, the firmware is written to then read this command list from memory and sort of start executing the commands one by one. And this is where we find our dispatch that we sort of wrote the command list from before. And the compute queue then can then sort of invoke waves and sort of start processing this dispatch. So we've seen that we can sort of write some command lists, some work to do from the CPU onto GPU memory, and then magically have the GPU execute that. So why can't we just do the same from the GPU itself? It's GPU memory, and that's exactly sort of what's happening with work graphs. With work graphs, we want to sort of continually write and read from these lists. So we can't just have the one long list. Instead, we can sort of use a ring buffer. And as we have multiple different nodes in our graphs, we can have one of those ring buffers for each of the different nodes. So in this case, we have an example graph with node A, B, C, and D. Node A can feed into node B and C, and node B and C itself themselves can feed into node D. We can then sort of modify the firmware on the compute queue to then sort of continuously scan these ring buffers for new work items, and then sort of decide on when to launch them and also how to launch them using the different launch modes. And this is, for example, how we can combine multiple of these work items, for example, for thread launch modes. So this all seems a bit easy. So let's just walk through one example and see how this goes. In this case, let's just say we have one record available for node A, which calls for 2 thread groups. So very easy, the compute queue can pick them up, launch 2 thread groups. In this case, we say, okay, each thread group occupies a single SIMD. Obviously, in reality, each SIMD could hold many more thread groups, but this is sort of a simplified example. Each of those thread groups can then themselves generate output for the nodes B and C. And we can then sort of use some atomics to increment the sort of counter in the ring buffer, and then just write those records to those ring buffers. We can do the same thing for the second thread group, and now sort of all the records have been written to the ring buffers. We have finished working on node A, and the compute queue can once again sort of scan through all the ring buffers, see, okay, there's some work available for node C and D, let's just go ahead and launch that. And of course, we have sort of the same game repeating again. Each of those thread groups will generate some work items for node D, which you can see here. And we can again start writing them to the ring buffer for node D one at a time. Until something bad happened, because now we sort of run out of memory in the ring buffer for node D. And to make matters worse, we also ran out of space in the GPU to start sort of carving away at the work in node D in order to free space in the ring buffer. So maybe work graphs isn't that easy after all. So we obviously must have missed something, because this sort of deadlock scenario can't happen with a work graph. Let's go back a few steps on when we decided to launch sort of the work items for node B and C. And see, with work graphs, you have to guarantee that every work item which goes into the graph can completely finish processing until sort of the leaf node, which would in this case be node D. And we call this for progress guarantees. And we need to find a way to ensure that these deadlocks can't happen again. And if we look at, for example, the first work item in the ring buffer for node B, we know from the output declarations of node B that it can at most write 2 records for node D. So if we want to prevent this sort of overfilling of ring buffer for node D, can just make a small reservation and say, okay, whenever we launch a thread group for node B, we just have to keep in mind that it might write 2 records to node D, so we need to check that the space is available at all times. We can do the same thing for all the other work items in node B, ring buffer for node B, until we completely finish launching them. And now we see that the ring buffer for node D is sort of completely filled up with reservations. And that's exactly how we mitigate sort of the deadlock we had before. Because now we can't sort of add any more reservations to the ring buffer for node D, meaning we can't actually start launching the work for node C until sort of node D has finished processing. Or we know the actual output counts that node B will write to the ring buffer. In this case, sort of the overall occupancy of the GPU is now limited by the size of the ring buffer of node D. Of course, in this small example, the ring buffers are very small. In reality, the work graph runtime would size them in order to always be able to fill the entire GPU. Now, we've seen how sort of the normal compute nodes can be programmed, can flow through the graph, and how we can sort of mitigate bad things happening when executing them. And I mentioned before that many graphics programmers have this long-lived dream of being able to also draw directly from the GPU, or actually draw codes directly on the GPU. And this is what the mesh nodes feature enables for work graphs. It's sort of a new recent addition, and as of sort of, I think, 1.5 weeks ago, it's in public preview, so you can also try it if you have a compatible GPU. So let's see how we can sort of make that work as well. Well, a mesh node essentially adds a new node launch mode called mesh, and that's very similar to just launching a normal mesh shader. These nodes always have to be leaf nodes, and the mesh node launch could be sort of related or is very similar to the broadcasting node, in that it sort of also launches a grid of thread nodes, thread groups. And the nice thing with this is you can have different mesh shaders with sort of different PSOs. So there has to be some sort of PSO switching in there as well. So let's take a look at how that works. Here we have a sort of very similar graph, or simple graph. We have just one sort of normal compute node and one mesh node. The compute node is launching the mesh node. We've seen before that for the compute nodes, we sort of have this compute queue, which is continuing monitoring the ring buffer and launching them. But for the mesh nodes, those have to be launched by the graphics queues, because there's graphics state involved. You have to do the PSO switching. You have to sort of set up all the other things that's required for drawing. The nice thing here is that these graphics queues are also sort of programmable by firmware, so we can sort of apply the same tricks that we used for the compute nodes here. But this would mean now that we have sort of a graphics and compute queue working at the same time, and for them to sort of get along nicely, the microengine scheduler can launch them in what's called a gang submit, which sort of joins the two together and says, okay, you now work together on this work graph. And they sort of can split the work between them, where the compute node queue still sort of checks all the compute nodes, launches them, and the graphics node sort of, the graphics queue only checks for the mesh nodes. So we can have sort of graphics or mesh node records going into the graphics queue, and can have mesh shaders launched on the GPU. So this sort of completes draw calls directly from the GPU. And obviously, each of those mesh shaders also can output triangles to the rasterizer. Those have to be processed by a pixel shader at some point. The sort of whole mechanism for launching pixel shaders is still running sort of in the background. That's completely detached from any of those two queues that I mentioned. And we still have the compute queue active, so the GPU can sort of continue decide on trying to fill itself with as much work as possible and running sort of compute work and graphics work side by side without any sort of barriers or other things that you explicitly need to add in order to make this sort of magic work. And you've seen this in Bastian's talk and sort of how this can be used to procedurally generate the entire world. So to summarize, we've seen that work graphs are GPU-driven producer-consumer networks. There is GPU-managed memory for the records, and there is sort of special features happening so that you can never run out of this GPU-managed memory. If you want to learn more about work graphs, we have some blog posts, samples, and obviously the paper you've just seen available over on gpuopen.com, so be sure to check that out. And this is sort of where you come in. We want to hear from you. What do you or what are your ideas for work graphs? You've seen sort of a glimpse at the specification now, what you can do with work graphs already. Are there any features we're missing? Do you have any sort of feedback, suggestions? Either come up to me or Bastian. We're still here at the conference for the next days. We'll also be at SIGGRAPH. So if you see us, just come up to us, talk to us, or just write me an email. With we want to hear what you want to do with work graphs, or if you have any ideas on sort of how we can still keep evolving work graphs, because as you've seen, it's still a sort of very active and alive standard that's continually evolving. Yeah. There's some reading homework, and I think with that, we'll have some time for questions.
Questions for Max?
So, two questions in one. What are the current plans for interoperability with both ray tracing and DirectML in the future?
So ray tracing, you can just use ray queries directly inside work graphs. And then, for example, for your ray tracing, you could connect up the material shading I showed before to whatever you hit. So if you just trace a ray, you hit some material, you can sort of use that to do material shading. As for sort of the whole DXR 1.0 stack with the sort of different shaders, that might come to work graphs, might not. It's kind of hard to integrate those two together. Same probably goes for DirectML.
Other questions?
Yeah. Would you want to shout?
Yeah.
Or?
You said that you're sizing the buffer so you can always fill the GPU at time. For like the demo, the previous talk, how much DRAM is there?
Okay, question was, I said before that we're sizing those ring buffers in order to fill the entire GPU. And the question was for the demo that Bastian showed, what would be some actual numbers? If I remember correctly, it was 196 megabytes of sort of backing. It's called backing memory for work graphs. The nice thing of this is it's actually constant. I have some slides if you're interested. This is sort of a different example. This is a computer rasterizer sample you can find on gpopen.com. Similar problem, you're not classifying by material, you're classifying by triangle size. So however many pixels those take up. And for example, if you only want to rasterize a small number of triangles, in this case, I think the original sponsor scene is at 81,000 triangles, you can see that work graphs, the backing memory requirement for those is sort of exceeds the one you would need for execute indirect. But sort of computer graphics has come a long way. So if you switch to a more detailed scene, you can see that the work graph's backing memory is actually independent of the workload size. In this case, you can see the sort of point of having work graphs and this constant backing memory. And I'd say in both cases, it's a couple hundred megs is justifiable.
There might be another question. Yeah.
Okay, if I got the question correct, you said in CUDA it's a bit easier to launch the different kernels, and WorkGraph seems a bit more involved with declaring what's the worst case you expect. I'm not sure if CUDA has this sort of managed memory as well, because WorkGraphs isn't just I want to launch new work. I have a work record or work item. I have some data to go along with that launch, and WorkGraphs will keep track of this memory for you. You need sort of these limits in order to keep deadlocks from happening.
So is it because CUDA has forward guarantee and DirectX don't have that?
WorkGraphs also has forward progress guarantees. I'm not too familiar with sort of the CUDA alternative, so I can't really say why their sort of API is similar. A lot more questions, yeah?
When you have the node array, is that, if you've got a node array and it's got like
there is some question was if we have node arrays, and I showed a slide where it says 1,000 for the node array size. Would that mean that we have 1,000 of these ring buffers in sort of a very primitive implementation you might have, but there are some optimizations you can do for node arrays. Yeah.
What happens to your cache subsystem? So there's no barriers, no memory fences or anything. So you have L2, but what happens above L2? So you just wipe it out? Because how do you track dependencies in your implementation across?
So the question was on caches and sort of the memory writes to ring buffers, if I got that right. How does it interfere with caches? So if you write to the ring buffer, they live in global memory. If you want to ensure that sort of the command process reads the current state, you would always need to bypass caches. And then if you want to optimize, yeah, that's probably the best way to.
So basically to send data from one node to another, there won't be any cache.
With this, you could keep them in caches. You could sort of move some of the ring buffers to caches.
Yeah, I'm sorry. So further question is
we can talk offline.
Yeah, offline. Yeah, please.
I think we're also on time.
Yeah.
If you have more questions, just come to me.
Yeah. Thanks again, speakers. Yeah.